This visualization represents a linear search algorithm attempting to process a massive data set. It evaluates exactly one data point at a time. On an array of 10 items, this sequential processing is trivial, but as the dataset grows to millions or billions of elements, evaluating every single item creates a severe computational bottleneck, causing processing times to scale linearly with the volume of data. To process data at this scale, we have to abandon the linear approach. Instead, we take the initial monolithic problem and repeatedly fracture it. By cutting the data space in half over and over, we create rapidly shrinking subproblems that scale logarithmically rather than linearly. This strategy is known as divide and conquer. It operates as a foundational algorithm design methodology, where large, unmanageable datasets are recursively broken down into smaller pieces, solved individually, and then reassembled. By isolating the 3 structural steps of this strategy and mapping them to a mathematical recurrence relation, we can quantify the exact efficiency gains made possible by this recursive architecture. Every divide and conquer algorithm operates by executing 3 strictly defined phases in sequence: divide, conquer, and combine. Looking at this array of 8 unsorted numbers, we begin with the divide phase. The algorithm does not attempt to sort the full set at once. Instead, it bisects the entire input space, splitting the single 8-element array into 2 distinct blocks of 4. Next is the conquer phase. The algorithm applies the exact same division logic recursively. The blocks of 4 fracture into pairs, and the pairs fracture into individual, isolated elements. At this stage, we reach our base cases. Since an array of 1 element is already ordered, the subproblems have become trivial enough to be solved directly. Finally, the algorithm enters the combine phase. The single elements merge backward up the execution chain. 7 and 8 combine into a sorted pair. 5 and 6 form another. These pairs merge into sorted blocks of 4, continuing until the entire dataset is reassembled into a fully ordered array. Tracing the path of those splits and merges reveals a permanent decision hierarchy. The exact steps create a strictly branching recursion tree, mapping how the initial data was fractured and reassembled. Structuring the execution this way reduces computational complexity. The algorithm runs its operations on tiny, isolated nodes, instead of continuously scanning heavy, monolithic blocks of data. This visual recursion tree dictates exactly how fast the program will run. Because the geometric fracturing follows strict rules, its behavior can be precisely quantified and analyzed mathematically. This is the general recurrence relation. It serves as a quantitative model for T of n, expressing the total runtime of an algorithm as the sum of its recursive components and its merging overhead. The variable a represents the number of subproblems. It defines exactly how many recursive paths, or branches, the algorithm creates at each step of the division. The variable b is the division factor, determining the rate at which the input space shrinks. If we cut our dataset in half, b is 2, dictating that each isolated subproblem processes an input size of n divided by 2. The final term, f of n, accounts for the combining work. This quantifies the computational cost required to merge the partial solved subproblems back together into a final output. An algorithm's efficiency is governed by the mathematical tension between these variables, the depth of the recursion tree on one side, and the processing overhead spent during the merge phase on the other. We see this tension clearly in binary search. It is one of the purest applications of the paradigm, operating by aggressively halving a target search space. In this sorted array of 7 elements, if we search for 60, we check the middle element, 40. Since 60 is larger, we isolate the right side and discard the entire left half. Mapping this to our equation, A is 1 because we only follow one recursive path, B is 2 because we cut the data in half, and f of n is 1 because there is no merge work. We simply stop when the target is found. Because we discard half the input data at every step, the execution or computational burden, as they are required to explore and arrange every single piece of data provided. This visual maps merge sort onto our recurrence equation. It still shrinks the data by half, keeping B at 2, but because it must sort both halves, A becomes 2, spawning 2 recursive branches. Combining the sorted halves then requires a linear scan through the elements, setting f of n to n. This yields an overall time complexity of O of n log n. Quicksort approaches data sorting differently by establishing a pivot to partition elements, yet it utilizes a similar recursive branching logic to achieve that same O of n log n average complexity. This mathematical mapping extends to complex operations like matrix multiplication. Under standard iterative methods, multiplying massive matrices scales poorly, hitting a cubic time limit of O of n cubed. This comparison illustrates Strassen's algorithm, which uses divide and conquer to restructure the matrix math. By strategically combining specific matrix quadrants, Strassen executes the operation using 7 multiplications instead of 8. In our equation, the A variable drops from 8 to 7, pulling the overall complexity down to O of n to the power of 2.807. Dropping a single recursive branch reduces the total volume of computations generated at every subsequent level of the tree. At the scale of millions of data points, these optimizations compound to yield significant gains in processing speed. These significant improvements in execution time are not without consequence. The same recursive structure that accelerates processing also introduces a specific burden on the system's physical memory. Every single time an algorithm divides a problem, the system generates recursive overhead. It must pause the parent function and hold its exact state in memory while it waits for the newly created subproblems to execute down to their base cases. Looking at this diagram of a memory stack frame, we see the physical impact of that overhead accumulating. Algorithms like merge sort exacerbate this by requiring separate, duplicated arrays to hold the data as it recombines. By implementing a divide and conquer architecture, engineers are making a deliberate calculation, sacrificing a portion of the spatial memory footprint in order to achieve these radical optimizations in runtime. The core operational model remains consistent regardless of the specific algorithm. Computational bottlenecks are bypassed through recursive structural fracturing. By mapping the 3 precise steps, divide, conquer, and combine, directly to the variables of the general recurrence framework, software engineers can accurately predict the true runtime of a data operation. In our next module, we will pull this theoretical model down to the practical level and trace the line-by-line execution mechanics of binary search. Divide and conquer forms the mathematical bedrock that allows modern search protocols, large-scale sorting arrays, and big data computations to process information with the efficiency required for modern applications.